Hello friends, welcome back. In this video, we're going to talk about extreme values and saddle points and how we can define them as well as find them with multivariable functions. So going back to Calc 1, when our functions just were all drawn on a piece of paper and were nice smooth curves, we could find those max and min values by setting the derivative, which represented the slope of the tangent line, equal to 0. And when we had these horizontal tangent lines, that was where we were able to define or determine that there might be a max or min. And then we had some tests, like the second derivative test for extrema, to let us know if that was a max or a min value. So in Calc 3, instead of a tangent line, we'll have a tangent plane. So right here at this tip, that appears to be a local relative maximum value. And if we were to draw some plane, the tangent plane here at this maximum would have to be exactly horizontal, right? If I gave that plane, even though I'm drawing it as a line, if I gave that plane any sort of tilt at all, eventually it would come down and intersect the surface, right? Might be further out. It could be intersecting, way down here. And what you want to remember, in Calc 3, these surfaces, they extend in all directions. So if that plane up here, this is like a big sheet of paper or a plane, if it has any tilt at all, it might go down and intersect the surface, and then it wouldn't be tangent. So we're going to be now moving to tangent lines instead of tangent planes. So we're going to redefine extreme values. We have a first derivative test for extreme values as well as a second derivative test for extreme values. And it's all going to look really similar to things that we have learned before. It's just a little bit different because we got to tweak it so that it fits in our thought process with multivariable functions. So here we have our definition for local max and local min, but we're dealing with multivariable functions. So we say we have this function defined on a region instead of, we would say, interval in Calc 1, containing some ordered pair. And if I take that ordered pair and plug it into the function, we can say that it's a max if that output, f of ab, if that is greater than all of the other function values, greater than or equal to all of the other function values, and those function values exist in the domain of xy points that are on this open disk, essentially the region centered around AB. Same for the local min. If those output values are less than or equal to all of the other output values, that represents a local minimum. And you can see this bumpy surface here. We can identify two potential maximum values. They are local maxima and then a local minimum value down here at the bottom. So with that word local or relative, they mean the same thing. It just means, hey, nearby this one point that we're considering, this is the highest point in this region. So for example, if we had just seen this part of the picture, you guys would tell me that this point on top of the mountain represents the maximum. But when we zoom out and we see a greater piece of this surface, now we can see that highest value is occurring at this top of this mountain peak. All right, so you can have more than one local extrema, but you can only have one absolute extrema. And we get to that a little bit later in this section. Next, we have a theorem. It's the first derivative test for local extreme values. So if a function has a local max or min somewhere at this point AB in the domain, as long as those first partial derivatives exist and can be found, we can set the partial of f with respect to x at the point equal to 0, same with the partial of y, or the partial of f with respect to y at the point equal to 0. And that's going to help us find, these two values are going to help us to determine critical points. So you may have remembered we found critical points or critical numbers in Calc 1. Those were found by setting the derivative equal to 0. They were also found when the derivative was undefined or the function was undefined. So any point inside the domain of the multivariable function where both of the partials are 0, or where one or both of those partials does not exist, those are going to give us critical points. And so I'm pulling in one other definition here. We're going to talk about saddle points. Did we graph a saddle-shaped figure a few sections ago when we were talking about our quadric surfaces? Remember the hyperbolic paraboloid, and I described that as being a saddle shape? So we'll talk about a saddle point. A saddle point is very similar to an inflection value for a function in Calc 1. So remember, inflection values are where the concavity changes. So where we were changing from concave down, in this case, to concave up. We had that inflection point. So saddle points are a little bit different, but it occurs potentially at a critical point where if in every open disk centered at that point, there are domain points, x, y, where the outputs are greater than the outputs defined at that critical point, and there are domain points where the outputs are less than the function value evaluated at that critical point. So that corresponding point, a, b, and z, being a function of a, b, on that surface is called a saddle point. And let me pull in the figure. Here we have two surfaces that have saddles at the origin. So if you look at this, if I were to slice through here with a plane on this first figure, I would create that parabolic shape that's concave up. But if I had chosen to slice through it somewhere different, maybe over here, that slice would be concave down. So it's like where we have those changes in concavity meeting. And I think it's a little easier to see on this second picture. So you'll notice that if I traveled along the x-axis and traced this curve, I would have a parabola opening down, concave down. Whereas if I trace along the y-axis here, we've got some concave up. And so when we have those changes in concavity in these different traces, and they're all occurring at the same point, that represents a saddle point. So the critical numbers will tell us if there is a local / relative, meaning the same word, so a local max or a local min, any relative extrema, and then as well as a saddle point. And we can test that using a second derivative test to help us determine what those points do represent on this surface in space. And we'll get to that a little bit later. So I'm going to do one short example in this video. For this example, we're going to look at calculating the local extreme values. So our multivariable function is x squared plus y squared minus 4y plus 9. In order to do this, we need to find the critical numbers or the critical points. And those are going to occur when we set that first partial derivative with respect to both of those independent variables, x and y, equal to 0. So my partial of the function with respect to x is 2x, and my partial of this function with respect to y is 2y minus 4. If I set this equal to 0, I get x equals 0. Setting this guy equal to 0, 0 equals 2y minus 4. I get y equals positive 4 over 2, 2. So in this situation, we have an XY value. There's only one possibility, and the only possibility is at the point 0, 2. So this is a critical point. It could be a local max and it could be a local min, or it could be a local min, I should say. It could be a maximum or a minimum value. And we can verify that with the second derivative test, but for now I'm just going to show you a graph of this surface and that we can let us visualize that there really is a min at that ordered pair 0, 2. So here is my surface, and you can see at x equals 0, y equals 2 right here. There's my local minimum value. So in this case, it's a minimum. Like I said, moving forward, we're going to talk about how we can determine if that's a max or a min without creating the physical graph. All right, email me if you have questions.